Hi everyone, following my original lecture plan, the transient simulation is considered in a single lecture. However, I have found that it's not that simple. So in this lecture 16, I will just consider a sinusoidal voltage source for the transient simulation. The transient simulation capability can be easily studied with a simple RC circuit. Therefore, in this part, we will consider a circuit having only lumped elements. In other words, we have no semiconductor device here. This is a part describing a serial RC circuit. The resistor is 1 kilo ohm and the capacitor is 1 picofarad. Also, circuit is quite simple, nothing special. Then how can you control the time? Only with these lumped elements it is not possible. We need an additional thing to control the time. A thing type chronos is introduced for that purpose. It just remembers the current time instance and a list of past time instances. Of course, in order to perform the transient simulation, our law should have an equation. Its type is just time. You must specify the name of chronos type thing here. A body keyword, Euler, means that the backward Euler method is used for the time marching. Now, let's apply a sinusoidal signal. Up to now, for voltage source, only its DC component has been specified. In order to specify a sinusoidal voltage source, we need other commands. The set command is used for this purpose with these two lines. The input voltage source Vin has a sine wave with an amplitude of 1.0 volt and a frequency of 100 MHz. We have other options. For example, a cosine signal can be specified. However, maybe you wanted to have a general piecewise linear waveform. It will be discussed in the next lecture. For a while, just concentrate on sinusoidal waveforms. We have a chronos thing. We have a correct equation set. Also, our voltage source has the sinusoidal waveform. Now, we are ready to solve a transient problem. Since the transient problem is related with an increase of time variable, when we solve a transient problem, the time variable should be a goal. Then, just like a bias damping procedure, the time will be changed. In this example, the time changes from its initial value to 100 nanoseconds. If the initial time is 0, then a constant time step is 0.2 nanosecond because the time step value is 0.002 and the goal value is 100 nanosecond. 100 nanosecond is corresponding to 10 periods of the input signal. As we know, the voltage transfer is given as 1 over 1 plus j omega RC. The serial RC circuit is a low-pass filter. Here, RC time is 1 nanosecond. This figure shows the voltage waveforms. The green one is the input signal. The red one is the output voltage. Remember that the frequency is 100 MHz. Using these parameters, you can check the result. Also, the Y parameter can be calculated. The analytic solution is given as j omega c divided by 1 plus j omega RC. This analytic solution is drawn as a blue curve. Also, at three frequencies, 10 MHz, 100 MHz, and 1 GHz, the Y parameter is calculated from the simulation result. Of course, the Y parameter itself is a complex number, and in this figure, only its absolute value is drawn. As expected, a good agreement is obtained. How perfect is it? By changing the number of time instances per period, you can feel the impact of time discretization. Now, let's move to the CMOS inverter. Of course, in this example, we have two semiconductor devices. In this lecture, we calculate the fan-out capacitance. Since we consider a chain of inverters, an inverter is used as a load of the previous stage. The capacitance is estimated from the Y parameter. Then, how can we calculate the Y parameter? First, a DC solution is obtained. It was done in our previous lecture 15. After that, a transient simulation is performed. After some periods, the initial response is diminished and we will get the small signal response. From that small signal response, estimate the Y parameter. Since we are considering a small signal response, the amplitude is set to be as small as 1 millivolt. A relatively low frequency, 1 MHz, is used and the DC input voltage is 0. So, the N MOSFET is turned off and only the P MOSFET is turned on. This figure shows the gate current of the N MOSFET and the P MOSFET. We can see that the gate current is following the cosine function. It means that the capacitive component is dominant. From these two curves, we can estimate that the Y parameter is about 1 nanosiemens. The capacitance is estimated as 0.167 femtofarad. It is noted that the gate capacitance of each transistor is 0.13 femtofarad. That's it for this lecture 16. In this lecture, the transient simulation capability has been introduced. The switching simulation will be performed in the next lecture. In order to simulate the switching behavior, the input voltage should be a pulse. The way to specify a pulse signal will be discussed. Thank you and see you later.